Alrighty, welcome everyone. So today is our continuation based on the last class. Last class we have been going here, right? We call full state feedback. This is about the main knowledge point of chapter the topic 4. As we know, topic 4 has three different major topics. The first topic is LQR. We talk about in class. The second topic is MPC. We also talk about it. And also for both LQR and MPC, we did class engagement. So it's self-balancing robot. And I think most of you should be fairly impressed for LQR and MPC performance because you were like in like a feedback class before, right? As you know, the LQR and MPC is just very hard to be balanced, especially for the self-balancing robot is really hard to be self-balanced because it requires the use of the PID and is very hard to tune because this inverse pendulum model. Even just one motor, I just super hard to tune. Okay, is barely people can do it. As you can see, LQR and PC they're very good, right? So now we come to after LQR and PC, we come to the third knowledge point, which we call full state feedback control. Of course, the full state feedback control has their nickname. The full state feedback control, right? The nickname called pole placement. I think about a month ago almost, we talked about pole placement, right? Remember that? Pole placement, the reason we call pole placement is we want to place our desired poles in particular location. So that we can satisfy their settling time and overshoot. Because we know based on user requirements, we know their settlement time requirement, right? Say 1.2 seconds. We also know the overshoot requirement. These are two things we know. However, is we do not know their pose. And as we know from your class feedback, right? We know as long as we know the overshoot, as long as we know the setting time, we can calculate the pole. If we can calculate a pose, which is able to satisfy the setting time and as well as overshoot, that means we can satisfy entire system. Now the question becomes how we can design A, B, C, D, the K stuff, right? We know A, B, C, D, right? We don't know K, right? How we can design K here to make this system X dot equal to AS plus BU, this system, their pole matching the desired pole. So now it comes to the question, what's desired pose? Desired pose here is the desired pose here. Let me write something here, okay, so you can follow better. The desired pose, we know desired pose from user requirement, right? Including settling time and overshoot. Spelling error, yeah. So our goal is to match. Our goal is to match the designed K feedback K, right? To satisfy the desired pose. You may say, oh, how the K satisfy this desired pose? How the K even relevant to desired pose? And of course, we know it's relevant, right? We know it's relevant. We know it's relevant. The way we know relevant is because we need to do a little bit of mathematics here. Based on this diagram here, right? We know this is B, the U, right? U. U is really, for example, the motor, right? The input. For example, the torque or the speed, right? For example, those things, right? The U is R minus Kx, correct? R minus Kx is equal to U, which is the motor input. As we know, this part is straightforward. Is A plus BAX A multiply X A multiply X. Okay, multiply X. AX plus BU equal to X dot. X dot integral is X. Y equal to CX. Y equal to C multiple X, right? Y equal to CX. Is where du. Du is, D often zero matrix, right? D often zero as as you remember. See, this is what it says here, right? Right. Sorry, there's noise because yeah, I apologize. And there's some noise in my family here. Okay. X dot equal to AX plus BU. U is R minus KX. Right? I'll show you the derivation process and how to make a bridge, connect bridge between K and desired poles, okay? Actually, you can think of if make a K match desired poles, that means this system here, right? Especially this system, it means closed loop, right? Let's talk about this line here and this line, how they relate, okay? And sometimes students feel a little bit confused for this portion. Oh, how they connected? How would that mean? Is any relationship between them? Yes, they do. Let me show you how they related, okay? So you can understand better. Great. How we can design K, which this K here, right? How they can match desired poles? That means what? That means simply this space, this feedback system, pole location equal to desired poles. Right? If you say, what that means? Oh, let me briefly explain to you, okay? Yes. So so we want to design K satisfy desired pole, right? Why? Because as if we set desired poles, we can satisfy desired certain time desired overshoot. If we say the K satisfies this desired pole, that means the feedback system pole location equal to desired pole location. Fair enough, right? This pole location here, how we know this feedback? I mean, what do you mean by feedback? Because K, right? Because K, right? A minus BK, right? Is why A minus BK? Because here we know U is R minus KX, right? We collect terms. We collect B minus KX, move this, combining this term together, called A minus BK. A minus BK, right? This AX plus BR is new feedback system state space. Remember, open loop is AX plus BU. Closed loop, A minus BK X plus BR. is, oh, this formulation different from LQR, also different from MPC, right? Where's optimization process goes? Sorry, guys, there's no optimization, unfortunately. And this pole placement is perfectly just like a theoretical little bit. So what do you mean by theoretical? Theoretical means you have no desired pole location. Then you match poles, right? There's no optimization process. However, if you know desired pole location, right? That means very likely we can calculate K here. Unfortunately, this thing here not as fancy as MPC. MPC is optimal, right? Number one. Number two is also can consider disturbance. And here, nothing about that. I mean, disturbance, no, sorry, right? And optimization, no. So it's very hard, rigid matching process. And makes sense to you? It's just matching your system pole, which is feedback system, right, to desired poles. All right. Anyone questions? Let me pause a little bit. Anyone questions? Time to ask. This is actually very important. Luke, any questions?
No, sir.
Alex?
No, I think good. Appreciate it.
All right, thank you. So, Caleb, Brian, Josh?
I'm good.
No question, right? Great. Dylan? Trevor?
As well.
I'm
Yeah, this
good.
is absolutely crucial. People are confused this time sometime, right? So I don't know what to talk about. Desired pole, system pole, what? Desired pole, clearly, right? From your your setting time, right? As long as user gave you a certain time, right? You say, oh, why user give certain time? Why user gave you overshoot? I mean, come on. You have to know, right? If you are a boss, like I'm a boss, I want design system. Number one thing, I need to tell you what's on my overshoot. I can tell you my certain time. Why? Because this is my desired. This is known, by the way. This is known. And this is unknown. This is unknown. But not totally unknown. The only thing unknown here is K. A no, B no, BR no, right? Everything is no here. R, of course, no. R reference. Your desired. I mean, this desired, not desired pose, right? These are temperature, these are depth, these are location, these are height, these are pressure. Remember, we press a lot, including next week exam. We do same thing. We block diagram is very absolutely crucial. You have to know that, okay? If you don't know block diagram, you lose points, okay? Please know block diagram. Alrighty, so only here unknown. See, we make this one here on left side. These are poles on the right side. They matched. You can solve this system pole here, right? Because this system, right, is a little bit more complicated. Okay, how can solve poles? It's hard to solve, right? I mean, it's hard to solve. People don't typically solve. This is A, this is B, right? This is K, blah blah blah. M and B K here. We typically solve determinant. We don't typically solve pole directly, right? I mean, pole is just the roots of your character equation, correct? Fair enough, right? You say, curve equation? What's curve equation? I don't know what we're talking about. Curve equation not that hard, right? Curve equation, remember? So it's just a denominator, the polynomial. This is to determine the SI minus A minus BK. Actually, Mills class did not talk about this. It's just a denominator value, right? Remember, in typical sense, we have S squared plus 2 e to omega n S plus omega n squared. Remember that, guys? That's a second order curve equation. This is generalized, although it's scary. When I look at the matrix, it's scary looking. But never mind. It's just essentially this thing for second order, S squared plus 2e omega s plus omega n square. However, if you write this n order, this is more generic term. But in mathematical form, it's determined Si minus A minus BK. That's all. If the roots, if somehow you can solve the roots, this second order curve equation, they should be equal to the desired roots, which is our pose. You see what I mean? This is a little bit beautiful here, okay? You see why beautiful? Because as long as we know the system like this, right? A minus BK here, right? And the curve equation here is just determine Si minus A minus BK. If we force this curve equation equal to desired curve equation, right? So now let's type here, okay? So our goal here is we want, type a little bit here, okay? Type make it a little bit, hopefully you can follow better. The feedback system characteristic equation should be equal to the desired characteristic equation. All right, let's copy this one here, okay? This is what we want, right? This part is what we want. And let me give you a follow through, right? Because we want this one here, right? We want this one here. This indicate, sorry. This indicate is this. This has that these two things are the same. These two things are the same. I make it bigger here, okay? Make it thicker, okay? I will revise slide so you can follow better and when you review the lectures. So these two things are the same. So desired feedback pole location equal to desired poles. That's indicate, and change the arrow here. I'll make this one here. Oh yeah. All right. These two same thing, right? Because if the pole same, the curve equation should be the same. Wrong spell. Everyone agree here or disagree? If I don't get it this point here, let me know, okay? So that means as long as the feedback curve equation, this one here equal to design curve equation, very good. So how do you know design curve equation? Design curve equation can be easily calculated from the S square plus 2e to omega n plus omega square, right? You say how you can calculate? You can calculate why? Because based on certain time, based on overshoot, which from user requirement, you can calculate e to omega n, right? Once you calculate e to omega n, then naturally you can, this is known, right? You say how come for not the second order, if the third order, fourth order, I mean, for that case, you had to guess. You had to guess two other poles. Two other poles can be calculated from their existing poles, right? For example, as we talked a month ago, so your let's say third pole, fourth pole, you can have thumb rule, right? Let's say what's the thumb rule? The third pole, the imaginary value, real value, right? Imaginary value, for example, now doesn't change, but real value is changing 10 times, 100 times, 1,000 times. You just multiply together. So desired curve equation, actually, you can calculate both from e to omega n, right? Damping ratio, certain time, right? Sorry. Hey, sorry, you scare me. I'm teaching class, please. So, thank you. Yeah, sorry about that. Right, so yeah, so the eta omega n, and so I can calculate from eta omega n, right? So also you can calculate from your desired poles, okay? Desired poles. Desired poles multiply together, right? You know from your class, right? Yeah, a couple poles. You multiply all the poles together, that's your desired curve equation. let me pose a little bit this. So anyone have question for this? This 3 slide are crucial, right? All right, now the third slide. So once you know this is a feedback system pose, right? Feedback system curve equation. And this is a desired curve equation. It's again, you say, well, how do you know desired curve equation? Because easily, right? Because you know the eta, you know omega n, right? Let's say second order. Then you know the desired, right? This is actually this is second order. This is 2 this dn minus 1 is 2 eta omega n, right? And yes, right. And this one, how d0 is omega n square, right? Let me write down here. Some student probably don't. Oh, eta omega n. What's that things? I forgot. Okay, let me write here. So, in order for the better. So d n minus 1 here, small d. Okay, is 2 is damping ratio. Multiply what? Natural frequency, right? And d0 here for second order system is what? Square. For second order system, okay? Right. If this is not so clear, and we can quickly give example, right? All right. So this is makes sense, right? For second order is 2 eta omega n, right? Eta means damping ratio, and natural frequency is like, you know, yeah, and hopefully you still remember, right? I'm not sure you remember, and hopefully you remember, okay? So yes, if you forget, I don't mind. I'll give you like a second order system. Just like this, right? Let me see, image here, image there, or no image, so we can give you a better idea, okay? Because look, this one here. Here, okay? You see, right? 2 eta omega s, right? Omega square, right? Omega square, right? This one. Sorry, let me, this look a little bit not very friendly. 1 second. Right, yes. Right,
You don't need your phone.
okay,
So now.
right. Right, yes. Like that here, okay? Right, this part is just this denominator is just characteristic equation, okay? Let me see. Just like here, okay? Let me highlight over here, okay? Fill. Right. You see what I mean here, guys, right? You see, and this is known, right? If this is known, so what you do is you make this part, this D thing match this A thing. This term, right? This term here matching this term because this is known. This A stuff is known. The only things are known. Therefore, you can solve K, right? So for second order, the match this one matches this one here, this one matches this one here, right? And this match a bunch of things. You can solve K, okay? Alrighty, so right, so here step number one, this is based on system feedback matrix. You solve this was system feedback state space, and then this system curve equation is this equation here. Determine SI minus BK, right? Then you just use determine SI minus BK, and you can calculate determinant. When you calculate determinant, you can calculate this curve equation, and this is unknown here. And this is known. Why known? Because based on second order, you can calculate this, right? If not second order, you can multiply a bunch of other poles to make this like any order. But how other poles, you can sum rule 10 times the 10 times faster, 100 times faster. You can make the real terms like 10 times faster, 100 times faster, right? Yes. Alrighty, so any questions? I think this is the theoretical part of pole placement. Any question about pole placement, guys? All right, if no questions, let's move on, okay? This example, right? Example is go back to all the time, right? The phase variable, observer, all those things. That's really the fundamental of this is like an optimal control, right? You see, there's no opposition here, unlike LQR and PC. I agree. Yes, no opposition. The way this one is a little bit different from optimization approach is this one is really based on we want to know the desired pole locations. And you say desired pole location is easy, right? Because we know the certain time we can calculate desired pole location, but this is for second order. But most of the system is probably third order, fifth order, right? For drones, we have sixth order, even 12th order. Actually, you already work on lab 3, right? You found that's pretty hard to make a 12 by 12 matrix work. So it's not that easy, by the way. It's not that easy. So this pole placement, although theoretically very interesting, is to solve real world system, it can be challenging. Why can be challenging? Because it's ideally solve a little bit low order system. Let's say it's third order, right? Or maybe the most fourth order system. In order to solve a 12 by 12 order, nearly infeasible. And in that case, you need to use LQR or MPC, okay? And this one, this is simpler stuff. It's really solving the low order system, simpler system, okay? For simpler system, it really work well, extremely well, by the way, extremely well. But the complex system is often does not work well. You have to use advanced controller, LQR or MPC, okay? For simple controller, which we do lab 4 soon, tomorrow, you can find, oh, look, this stuff works. Yes, it is working for simple systems. So for simple system, right, if you don't want to design like LQR and PC, right, you can use this called in MATLAB called place. MATLAB lab 3, actually, I'm not sure you realize in MATLAB, right? Whole place. Actually, all the stuff in MATLAB is just one command. Actually, you see this is MATLAB drawing, right? Actually, similar to almost identical to what you draw, right? The only difference they have D. We don't have D here. In your lecture, we don't have D, right? Why? Because often D is 0. You see apparently feed forward, right? We know the A system matrix, B input matrix, C output matrix, and D is feed forward, right? C is feed forward, and K feedback. And in MATLAB, just place command. Remember in LQR, in MATLAB, LQR, right? Right, look here. So MATLAB LQR, right? Actually, this stuff actually in MATLAB very easy. See, Q and R, right? We talk in class. MPC, right? MPC. Also one command. MPC here. We talk also in class, okay? So everything is one command actually in MATLAB. So if in MATLAB here, the place command as A and B and P, right? P your desired pose, okay? Once no desired pose, you know A, you know B, you can get the K, right? You see that right? But in this lecture here, I hopefully, in this lecture, hopefully, we can show what's behind the scene. You may ask, is it necessary we know the behind the scenes stuff? Is it useful or not quite useful? I mean, it's hard to say useful, right? I believe useful. Why useful? Because if you know hand calculation, you can calculate inside out. You know what's going on. For LQR and PC, we talk about in class, right? In contrast to pole placement, LQR and PC controller, we spent almost 3 weeks, right? It's just not possible for you to hand calculation. It's infeasible. It's really use computer stuff. The pole placement, in contrast to LQR and PC, you can do hand calculation. Why? Because simpler. Why simpler? Because you just matching the curve equation. That's all you do. As long as you match the curve equations from feedback system determine SM minus MVK, calculate determinant, and you try to match the value we desired here, and you can solve K. That's all. You say, wow, how simple it is. It is simple, but when you calculate determinant, it can be a little bit like a calculation heavy sometimes, determinant. Well, 2x2 matrix, 3x3 matrix, it's not that hard if you have calculator, okay? You can, if you use MATLAB, easy, okay? And you can use calculator to calculate, okay? Or use hand, right? We did like a determinant, I believe, right, in class. Alrighty, so I just conclude you the relationship between this LQR and PC and pole placement. Pole placement is simplest, okay? And which use this like a command here, okay? You can look at there here, get A, get B, get C, get D. If you know their pole location, let me see the pole. This is desired pole, so you can place it. You can calculate their K, right? So actually, we just one command here, okay? Alrighty, so in rather just like use a bunch of like MATLAB command to do things, I want to show you how we do behind. All right, this is first example. Given this first example, we know desired pole location, which is this. By the way, based on this three pole here, how much the size? What's the size of the state space? Anyone know? We have 3 poles here, right? What's the size of the state space? A matrix. Anyone know here?
A matrix would be a 3x3.
Absolutely. Awesome. 3x3 matrix. So the K value will be 3K here, right? K1, K2, and K3, right? Right, K1, K2, K3. Just be cautious, right? When you draw the arrow here, the reason called full state feedback, because if from all this X here go to U. You see why all X go to U? Because look at here, all the X here and go to U. Similarly is here, okay? All the X values and go to U. Right, go to U here, okay? And this is R, okay? So U is R minus KX. K3 S3, K2 S2, K1 S1, right? And right? So is U equal to R minus KX, okay? So this is your phase variable type, right? You see, phase variable type, I forgot a little bit. Go by rehearsal, okay? Right, 3x3 matrix with this desired pose. Once I know desired pose, actually desired curve equation is just this pole location. This pole multiplied together is a desired curve equation. All the pole multiplied together. Okay. Once you know that, and you can solve the k values. So let's go through step by step. So again, right? So we redraw this a little bit here. Right. Good. So from S1, S2, S3, S3 dot. Right. Think of the U. Right. And this one go to this here. Okay. All right. So we want to based on this flow diagram here, we can derive state space. You say how come? Because you know this like a flow diagram here, right? You know the flow diagram, right? You can draw this state space easily. Why easily? Because remember like before, right? Once you know that, you can draw like this. And so you know S1 dot equal to S2, S2 dot equal to S3. You see where got it, right? See here. S1 dot here, right? Equal to S2. S2 dot S3, right? Why S2 dot? Because it is integral here, okay? It's I forgot a little bit. It's time for you to rehearsal. What we talk about chapter 1? Topic 1, sorry. Topic like first topic, right? State space fundamentals, okay? So this S2 equal to S1 dot, S3 equal to S2 dot. S3 dot is S3 dot here, right? S3 dot is R minus K1 S1 plus K2 S2 plus K minus, right? This minus K3 S3, right? Right, you can list a bunch of equations on this, okay? Right, list a bunch of equations. You got this is a state space. Again, by looking at this state space, we clearly know this phase variable. Why phase variable? Because easy. Right? All right, now the follow on, right? Now the next step is try to force determine Si minus A minus Bk. Right? Calculate this one, right? Why calculate this one? Because as we know, we want to make this determined here equal to this desired. Then calculate k values. Therefore, we must calculate determinant here. Then you know the stuff here, right? You know this one here. You can calculate determinant A. This one is already called A minus Bk, right? The entire matrix called A minus Bk. Then you calculate determinant Si minus Bk, right? Just this S. I is identity matrix. Si is S00, S00, 0, S0, 0S. Why? You see, why is that? Because I is for I identity matrix in linear algebra is 1, 1, 1. Multiple S, right? Become this. A minus Bk is from here. A minus Bk, right? A minus Bk. Then determine Si minus A minus Bk become S cubic plus 5 plus K3 plus 4 minus K2 and plus K1. You see, how come you got this one here? I mean, calculate determinant. You calculate determinant. That's how I do. That's how I do, right? Calculate determinant. All right, you really need to calculate determinant, right? But for phase variable, we have a slight trick. For phase variable is this is a phase variable, right? This is phase variable. So we can like just simply move the last term to the front, the middle term to here, and the very beginning term to here, to last term. So that's the for phase variable, right? You see, I mean, what we're talking about? We talk about the determinant. There, if you say I'm very lazy, I don't want to calculate stuff. I just very bad at calculating matrix. I cannot calculate. Sorry. I mean, if you really forget how to calculate determinant, there's a shortcut for you. This 5 K3, you change the sign here, right? Move here. 4 plus K2, move here. K1 move here. You change the sign a little bit. That's how you do. However, this is not everything. We may want to calculate anyway. I mean, so if you don't want to calculate just very brute force, you can use shortcut. But shortcut, this shortcut, this correspondence is only hold for like only hold for phase variable type. Okay. Only hold for this one. See, last row, the last row is the non-zero term, right? This is called phase variable. Phase variable makes sense. If phase variable, there's shortcut like this, okay? If not phase variable, it's hard. So you just have to calculate determinant. Anyway, if you're able to calculate determinant, you're good. You can calculate this desired curve equation. Then you have desired curve equation and desired curve equation, right? This is desired curve equation, and this is your system curve equation. Then you can solve it, right? This is your system curve equation. How you calculate system curve equation? Because 3 poles, multiply 3 poles together. Pole number 1, s minus this. Pole number 2, s minus this. Pole number 3, s minus this. Right. So this is system curve equation. All 3 poles multiplied together. Right? You know this system pole. This is your desired pole, right? Sorry about that. This desired poles. All desired poles multiplied together, multiply the desired curve equation. Then this term, the second order term, is just equal to this. First order term, just equal to this. Zero order term, right? Zero order term, just equal to the R. And the match value, so okay, see that? So okay. Alrighty, so everyone please try to on your computer let's try to practice. I'm sitting here, and if you're able to finish, you can share a screen, okay? You're welcome to share a screen, please, okay? Once you finish, please share a screen, okay, guys, okay? Just this example, you can open lecture notes. You can follow the example, please. Write on your paper or so, in a way you can, if you're able to share screen, it'll be awesome, okay? Or ask me questions. So let's finish this example in class here, okay? Brian had a question, Brian? Brian? All right, Brian looks like a question. No question. Let me see. All right, great. And did push any questions? Dylan? Josh?
I'm good, sorry.
All right, perfect. Yes,
No,
Alex?
I'm all-
Thank you, Alex. Luke, Trevor?
Yes, I think I'm good.
I'm
Yeah,
good.
Thank
let's
you.
try. Yeah, great. Let's try to finish this example here, okay? So on Wednesday class, right after class, we start on board this question. So I'll ask people to do this question, okay? The tricky part, this one is maybe is actually a simple one. How you calculate the multiply together. Multiply together, remember g square equal to -1, okay? G square equal multiply 1, okay? G square is -1. And this how you calculate desired curve equation based on desired poles, okay? Right, let's try to finish this one here. We have a couple minutes. Let's finish, everyone, right? Just write a piece of paper there, okay? So anyone can share screen, that'd be awesome, okay? Or you can use picture, you can use a phone, take pictures, right? I mean, somehow that, you know, anyway. So, right, so this one here, you just redraw this diagram here on your paper. Then on your paper, you can list the state space. Well, how you can list state space? Because this flow diagram, as long as no flow diagram lists state space. Why can list state space? S2 equal S2 equal S1 dot, S2 equal to S2 equal to S2 dot, and S3 dot equal to R minus KX dot, okay? Based on this one here, you can list the state space. Why no state space? Because you want to calculate A minus BK. Why you want to calculate A minus BK? Because we want to calculate the determinant. Why you calculate determinant? Because we want to match. See the determinant here, right? Which is this feedback system curve equation, right? It match this one, but matching each term becomes okay. Actually, not that hard, okay? Raise your hand, right? Or like tell me anyhow. Let me know once you confused, or also let me know if you finished. Let's try to finish this one as much as we can in during this practice here, okay? This actually called pole placement. Is everything in front of you, right? You know the pole, right? You know the feedback systems, you know everything inside out. Actually, this is a big part, almost the 80% or 75%, at least 70% of like level 4, by the way. So tomorrow, actually, we do like a more complete example in lab here, okay? Right? Let's try to finish up this one, okay? This is one of the simplest example I can think of, right? You give 3 poles, you can calculate desired curve equation based on 3 poles. You see how? You easily can calculate based on their multiply, right? Right? You can multiply use S minus P1, multiply S minus P2, multiply S minus P3. Once you get that, you can easily continue, right? Right? So let's draw a diagram, right? Step number 1, step number 2, desired state space. Step number 3, calculate determinant. Right? Step number 4, step number 4, calculate the desired curve equation. Step number 5, matching it. Or you want to save time, right? So you can put step number 4, number 5 together, right? But you decide, okay? Generally 4 to 5 steps. We can see 5 steps for simple. Every step is simple example there, okay? Again, based on this question asks us, we know these are pole location. Please solve the full feedback control system. right? Give it 3 desired poles. Solve desired curve equation, right? Give this diagram here. You can solve determinant SI minus A minus BK, right? Which is able to give you the feedback system curve equation. So the goal here is to enable the feedback, right? Any other question, guys? So Alex, Josh, Brian,
Nope, all good.
I think our class almost done, right?
Yeah.
Yeah, I think I'm good. Thank you.
Good. Right. Yeah, so able to follow this example one, number 1 here?
Yeah, I think so. I just need a few minutes to go through it.
Perfect. Brian, you follow pretty well, Brian?
Yes, sir.
Perfect. Ahmed, you follow well, Ahmed?
What?
You follow this example here? This is chapter topic 4 pole placement. You
Yeah.
follow? Huh?
Yes.
Yes. Abdullah follow as well, Abdullah?
Yeah.
Right. This is for example, right? Then next class I'll ask you solve right almost immediately in the class, okay?
There's there's an test next Tuesday.
Yeah, there's test next Tuesday, correct. But it's not to do with this. But what I mean by the next class is the Wednesday, okay?
Yeah. Okay.
Yes, I want you to solve this like on board, guys, okay?
So the test will contains which topics?
Oh, that's a good question. I think let's go through here. The test. Second test guideline. One second. So second test guideline. See that? You see that? This one here?
Mhm.
Yes, I see.
Topic 1, topic 2, topic 3, okay?
Yes. Okay.
Topic 4 would not be on this this second test, okay?
Good.
All right.
Thank you.
Great. Thank you, thank you. So I think our class almost done. Any other questions? Thank you, thank you.
Yeah, I think I'm good. Appreciate it. Thank you.
Perfect. Thank you, Alice. Alice, how's it going, Alice?
Going good.
All right, perfect. And let me yeah, hold on a second, and